second session on C. So today I would like to talk a bit more about integers. All right, and we're going to go through all the data types and understand the relationship between them. You're going to see that mostly C, the data types are either integers of some form or doubles or real numbers, right, represented as single or double precision. Okay. And we're going to learn how to deal with that. Everything else is convertible. I mean, you can think of characters and strings, but they're essentially integers or sequences of integers. So we're going to write another piece of code, right, which I'm going to call int.c. And let's start with the usual .h. And for the time being, I don't need any arguments. I just want to discuss some stuff. And actually, before writing the program, let's talk a little bit about binary hexadecimal, right? Numerical basis of numeration. I'm not sure whether that was covered in earlier classes, math classes or whatever, right? We can count with any number of symbols, right? And typically we count with 10 symbols, which we call digits because they're 10. So by the way, it's not quite correct to call them binary digits or hexadecimal digits, even though this is a very common expression, right? But digits is related to the number 10, right? We have 10 fingers, and the word digit comes from Latin, and in Latin, digit means finger. So digits is kind of, requires to have 10 symbols, but nevertheless, we use the phrase binary digits or hexadecimal digits or octal digits, all right? So let's see how we would be able to count with only 2 digits, only 2 symbols, right? So I have 0, then I have 1, and then I have run out of symbols. So I'm going to move on to sequences of 2 binary digits, right? 1, 0, then 1, 1, right? And for conformity, I'm going to add prepend the 0 here, right? And I run out of numbers of 2 digits. So I'm going to move to numbers of 3 digits. 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And notice, so we luckily have a column number there, or a row number, right? 1, 2, 3, 4, right? But notice that these are not the correct row numbers, right? Because you should start counting from 0. So I should go from 0 to 7. But pretty much, if I take this number and I go here and subtract 1, I'm going to know which decimal number is represented by the string 101. Now, if I want to count further, right, it's actually a very simple algorithm. I can just duplicate this, right? And for the first 8, I can just add 0. And then for the next, I can just add prepend 1. Right? And I'm going to do it again because I actually want 32 numbers. So I'm going to leave a row here first because this is going to be zeros. And then here we're going to have ones. Okay, so obviously we can in principle ignore the the prepended zeros, right? So we can see very clearly that with one digit, I can express two numbers, right? With two digits, I can express four numbers, right? So 2 to the power of 2. With three digits, I can express 8 numbers, so 2 to the power of 3, and so on and so forth, right? So going to, with 5 digits, we can express 32 different numbers, all right? So let's do the same for base 8, octal, as we would call it, right? So we're going to start with 0, and we're going to need two digits, and I'm going to use 2 from the very beginning. 1, 2, 3, 4, 5, 6, 7. So I have run out of digits of single digit numbers, right? So because I only have 8, this is base 8. So the next one is going to be 1, 0. So again, we're going to continue 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Okay, 2, 0. Sorry. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, oops, 2, 7, 2, 8, 2, 9. Again, this is 3, 0, 3, 1. I never found base 8 very useful, but we're going to emphasize the relationship now. So for this particular purpose, it's quite educational. 36, 37, and that's it, right? So notice one thing, that for any number, if I separate these digits in groups of 3 and we only have 2 left, okay? So 3 and 2, right? The first, anywhere I go, right? The first, this binary number is the same as this decimal number, right? And this is a property of the fact that 8 is a power of 2, right? 8 is actually 2 to the third. So separating 3 digits, 3 octal digits, right? And then looking at them as 2 separate groups and then converting each separate group into decimal would actually give me the octal representation, right? And then typically we don't need to stop at 5. Let's say we have 6 digits, right? Then we'd have 2 groups of 3, right? So we convert the first group and then the second group separately, and we get the correct octal representation, right? If I have 9 digits, I can separate them in groups of 3. I would have 3 groups. I convert the first separately, the second separately, the third separately, and I get, right, I convert them into the decimal numbers, which are going to be 0 to 7, right? And when I put them together, I get the octal representation. So I'm going to put this back. So let's see what happens with base 16, which is actually a lot more interesting from a practical point of view. And we'll see very soon why, right? So base 8 is useful. Why? Because it makes the binary numbers smaller, right? And yet we can use only digits. We use 8 of the 10 digits available, right? So if I were to use a regular keyboard, a telephone keyboard, for inputting these numbers, which was happening a lot in the very early computers, I could use that, right? I only needed 8 digits to input octal numbers, all right? And then the conversion from binary to octal was relatively straightforward. right? Not as straightforward as it would be from binary to 10, base 10, right, to decimal. Let's see what, and the same thing is going to happen for hexadecimal, just that for hexadecimal, we need to separate into groups of 4, right? Because 16 is 2 to the power of 4. So let's get acquainted with the decimal, with the hexadecimal numbers. 0, 1, 2, 3, and if you're a hardcore C coder, you would know hexadecimal very well, right? 9. So we run out of the 10 digits. So for 11, we're going to have, did I count one twice? 0, 1, 2, 3, 4, 5, 6, 7. This is A. But A is not, A is 10. Yeah, okay. Then B, then C, then D, then E, then F. And now we have 16 symbols, right? So we have to move on to 2-digit numbers, right? So we're going to have 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, and 1, F. Okay, is that clear? All right, so the same principle applies. I can separate them into groups of 4 starting from the right, and then each group of 4 gets converted into the corresponding hexadecimal digit. So I can do this conversion irrespective of how many bits I have, right? If I have 32 bits, which is a very common case, and nowadays even more common is 64 bits, I separate them into groups of 4 starting from the right, and each group of 4 gets transcribed into the hexadecimal digit, right? And then I put all the hexadecimal digits together, and that's the number. So for conformity, we can add a 0 in front. All right. So these are numbers that are positive. All of them are positive, right? So I have 5 bits in the current case, and I can express 32 different numbers from 0 to 31. So it's not from 1 to 32, from 0 to 31, right? It's always from 0 to 2 to the power of n minus 1. Okay? So let's think of, counting. Counting means adding 1, right? So we start from 0, we keep adding 1, and we add 1, and we keep adding 1, and at some point I'm going to reach here, and then I want to add 1 to 31, to the number 31. What's going to be the result if I'm limited to 5 bits? Let's say I'm limited to 5 bits. What do you think the result is going to be? So normally if I had 6 bits, I will move on to 6-digit numbers, right? So I would have 1, 0, 0, 0, 0, 0, right? But I don't have the 6th bit, right? Which means that if I'm limited to 5 bits, and we will always be limited to some number of bits, right? There will be a number to which if I add 1, I go back to 0. Okay? So this is called overflow, right? And can be, if we code at the level of assembly language, we can actually detect that this happened, all right? But in C, we don't have that luxury. So that's a very interesting thing, that they didn't make it possible in C to check whether there was overflow, all right? So similarly, if I take 2 very large numbers, for instance, I take 22 and plus 24, right? So obviously the result is going to be 46, but 46 doesn't fit into 5 bits. So I'm going to compute the 6-bit result and throw away the 6-bit. So I'm going to get 46 minus 32, which is 14. Okay? So this is another case of overflow. Also, currently we are in the convention of representing only positive numbers. So if I perform a subtraction and I get a negative, the result would be negative. What do you think is going to be? What do you think the actual result inside the processor? What do you think it would be? So let's say I do 1 minus 2. I perform the subtraction 1 minus 2, right? What's the result? Assuming that I have only 5 bits. Yeah, so you're going to go back from the bottom, you're going to go back to the top, right? From the top to the bottom, right? So the result is going to be 31. All right? So that's the principle for integer arithmetic in all computers, right? Most languages hide that away from you. They're trying to make you unaware of that, and typically they put a number of bits in a number, right? In an integer, they put a number of bits that is large enough that you never get to experience that, right? But C was created to tackle the nitty-gritty, the internals of computers, right? So, for instance, if you deal with network packets, you want to compress your information as tightly as possible, so that as to minimize the amount of bandwidth that you're using, right? So speed across the the network is much lower than speed of transfer to the disk or to, for instance, between memory registers, right? So you want to minimize that. So you're going to reduce your information to 8 bits. You're going to make it much smaller than the typical number that you want to have. And at that point, whenever you do arithmetic, this kind of situations are going to occur very frequently. So we have to be careful. All right. So we're going to start playing with unsigned integers. All right. The typical size of an unsigned integer is 32 bits. All right. That's a relatively large number, but nevertheless limited. All right. So how can we create a number that is that large? So first of all, remember the fact that it's unsigned. So I'm going to introduce a new type of data, which is not very different from what you've seen last time, which was yesterday. So I'm going to say unsigned int a, and I'm going to give it the value 0x. So instead of using decimal, which is a bit more complicated in this case because you can't figure out the bits, I'm going to use hexadecimal. And hexadecimal numbers in C are first-class citizens, and they will be prefixed with this 0x symbol, right? So I was saying 32, right? So every F is 4 bits. So I have to have 8 of them. Okay? So this is 2 to the power 31. Okay? So let's do the following. We're going to print a %d, and then a plus a equals, let's have a semicolon here as a separator, and then we're going to have another %d here, and we're going to say a, and a plus a. Remember how this works, right? That this second argument will be inserted at the place of the first specifier, right? And this third argument will be inserted at the place of the second specifier. And let's see the value of a plus a, right? And actually, we need to tell printf that this is an unsigned number. So unsigned number, sorry, I can't use %d, I have to use %u. Okay, and we'll figure out all these quite shortly. So let's compile this. Int, not minus, minus o int. Okay, and I'm going to run int. Whoops. Oh yeah, that's correct. I should have put a backslash n here. So just to make it a bit clearer, let's try and make this, right? So look at the value of a. All right. So a is 2 to the power 31. Right? And that's a number that is not easy to remember in decimal. But look at a plus a. It's actually 1, it's equal to a minus 1, right? Right? Why is that? So we have 32 bits, right? And we have a plus a is a number that doesn't fit into 32 bits. Actually, we can figure out the value. So addition works exactly in the same way. So I'm going to do it for 4 bits. 1, 0, 0, 0. So let's say I have 4 bits. I have 1, 1, 1, 1, right? Plus 1, 1, 1, 1. And let me leave a space, right? So we can draw a line, as we used to do in primary school. And then we start from the back. 1 plus 1 is 2, which in base 2 is 10. So I have a 0, and I will carry 1, right? Now, for the next rank, I have 1 plus 1 plus the carry, which is 1, right? So that's going to be 3, which in base 2 is 1, 1. So I'm going to write a 1, and I will carry 1, right? Same here, right? It's going to be 3, which is 1, 1. So I'm going to write a 1 and carry 1. Same here. Write a 1 and carry 1. And then when I reach the first rank, I'm carrying 1, so it's going to be this, right? So notice what's happening, right? It's double, right? And I have 1, 1, 1, 0, right? It's double. Doubling in base 2 is essentially adding a 0, right? Because we're multiplying with 1, 0. 2 in base 2 is 1, 0, right? So as in any other bases, when we multiply by 1, 0, we just add a 0 to whatever we have. Okay? So we have a 5-bit number, but we don't have space for the 5th bit. So the 5th bit goes away. Right? So the 5th bit was here and now goes away. So what we get is a minus 1. Clear? So this is what happens. It's the fact that a plus a would take 33 bits to represent correctly, but we only have 32. Clear? Okay. All right. So let's continue and see what do we get. So I'm going to add another space here. I'm going to say 2 minus 1 equals %u. And let's see, 1 minus 2. And see how much this is. And we're going to write here 1 minus 2. So look at what the value of 1 minus 2 is. Okay? It's the same as this guy. Right? Because we decided to represent only positive numbers. Unsigned means without sign, therefore positive. Actually, non-negative if you want to be more specific, right? 0 is included as of that. Is this clear? Cool. All right. What do we do for negative numbers? Or how do we represent positive and negative numbers? So we actually have a bunch of solutions, only one of which is really elegant, right? But I can simply encode the sign as an extra, as one of the bits, right? So I can say, I'm going to use 31 bits for the value, and one of the bits, the 32nd, I'm going to use it for sign, right? And maybe 0 is plus, and 1, so that's a possibility. Okay, but what is used in practice, because it's a lot more elegant, is what we call complement of 2. Complement of 2. Okay, so and I'm gonna write the numbers from -8, -7, -6, and then we're going to see how we give them binary values. -5, -4,